We're now starting chapter 12, where we're discussing the concept of chemical bonding. So just as a refresher, ionic compounds are composed of a metal cation and a non-metal anion. And ionic compounds participate in what are known as ionic bonds, which is an electrostatic interaction, an attractive interaction between a cation and an anion. So for example, in sodium chloride, we have sodium plus, and this sodium plus experiences an attractive interaction with chloride, which is Cl minus. Now, the main thing that's important to know is that ionic bonds are very strong. We see this in the fact that ionic compounds have large melting points. If you actually try to melt sodium chloride and separate the ions from the solid, closely packed lattice, it takes a lot of energy. Ionic compounds typically melt around 400 degrees Celsius. Now, in terms of covalent compounds, covalent compounds are typically composed of two or more nonmetals. Now, a covalent bond involves the sharing of outermost electrons between two atoms. So for example, in hydrochloric acid, HCl, we have a sharing of our outermost or our valence electrons. So these are known as shared valence electrons, otherwise known as bonding electrons. So in covalent bonds, we are sharing electrons between two atoms, and it's these shared electrons that form the basis for this covalent bond. The reason why a covalent bond is stable is if you think of each of the nuclei of each of our two atoms as a bundle of positive charge, the electrons shared between our atoms are stabilized by this positive charge. So covalent bonds are stable, and however, covalent bonds are weaker than ionic bonds. Ionic bonds are substantially stronger than covalent bonds because this electrostatic interaction in an ionic bond is substantially more stable. Okay, so we've discussed and we've seen examples of ionic and covalent bonding before. That's why covalent compounds typically melt at relatively low temperatures. Now let's talk a little bit about bonding in relation to valence electrons. So we know from our previous discussion of ionization that atoms typically lose or share their most readily accessible electrons and their highest energy electrons, otherwise known as the valence electrons. Again, the valence electrons are the electrons with the largest N or the highest energy. Now, bonding and ionization generally follows what's known as the octet rule, which is this idea that atoms gain, lose, or share electrons to reach what's known as a noble gas configuration, which is 8 valence electrons. Now, the reason why we've taught abbreviated electron configurations in previous chapters is because abbreviated electron configurations are wonderful to help identify valence and core electrons. So let's take a look and let's just practice that skill, and let's write out the abbreviated electron configurations for a few elements, and let's identify our valence and core electrons. So I'm going to my periodic table and I find chlorine. The preceding noble gas is neon, and our configuration is 3s2 3p5. As we can see, we have 7 valence electrons, and chlorine is a group 7a element. Now, let's look at bromine. So bromine is argon, 4s2, 3d10, 4p5. And my question to all of you is, and this is important, how many valence electrons does bromine have? How many valence electrons does bromine have? And don't be shy to type your answers in the chat. 7, right. Only the electrons in the largest n-value orbitals, the electrons farthest from the nucleus, are considered valence electrons. So bromine also has 7 valence electrons, and it's also a 7A element. Does anyone see a bit of a connection? Does anyone see a relationship between the group number and the valence electrons? Are they the same or different? Is the group number the same or different compared to the number of valence electrons? So we have 2 group 7A elements and they have the same number of valence electrons. And this is important because elements in the same group also have the same number of valence electrons. So what I want everyone to do is to take a moment and to try to write out the abbreviated electron configurations for lithium and carbon and identify the valence electrons. Let's take about 3 minutes to work on this example, and then we'll come together as a group to discuss. And the responses I'm seeing in the chat look great so far. Let's try to get a few more responses and we'll discuss in about a minute and a half. Okay, so looking at lithium, our configuration is helium 2s1. So looking here, we clearly see we have 1 valence electron, and lithium is a 1A element. Carbon, we have helium 2s2, 2p2. We clearly see that we have 4 valence electrons, and carbon is a group 4A element. In general, main group elements have valence electrons equal to their group number. Now, we're especially interested in the valence electrons as they're responsible for bonding, reactivity, and other chemical properties. Okay, so we have a method for counting and identifying valence electrons. Wonderful. This is review from our previous chapters. Now, how can we use that? Well, Lewis dot structures provide a means of abbreviating the valence electrons using a dot to represent an electron, a valence electron. So 1 dot is 1 valence electron. So lithium is a 1A element. It has 1 valence electron. Beryllium is a 2A element, 2 valence electrons, 2 dots. Boron, 3A element, 3 dots. Carbon, 4A, nitrogen, 5A, oxygen, 6A, fluorine, 7A, neon, 8A. Okay, so what I want us to do now is to practice drawing out Lewis dot structures knowing that we can identify the number of valence electrons, and then from that information, draw dots to represent those valence electrons. So chlorine is a 7A element. So we have 7 valence electrons. So we have 7 valence electrons. So then we take chlorine and we draw 7 dots. Okay, perfect. Likewise, bromine is also a 7A element. So we have 7 valence electrons. Remember, this 7A is our group number. So then, in turn, we would draw 7 dots for bromine to represent 7 valence electrons. What I'd want everyone to do now is keeping in mind that this overview of Lewis dot structures for each of our groups in the periodic table can be applied to every element in that group. I would like you to write out and draw a Lewis dot structure for each of the 3 elements. And you're welcome to share your responses in the chat by indicating how many dots, how many valence electrons should I draw for each element. And then if you want, you can also use the annotate feature to try drawing out a Lewis dot structure. And we'll discuss in about a minute and a half. And the responses I'm seeing in the chat look great so far. Okay, so let's walk through. So for sodium, we have a 1A element, ergo we have 1 valence electron. So we draw sodium with 1 dot. Silicon is a 4A element, so we have 4 valence electrons. So we draw silicon with 4 dots. Traditionally, it's common to draw the first pair of the first 2 electrons as a pair, just to respect the fact that technically those first 2 electrons are going in an s orbital and they're paired in the s orbital. I know it seems a little pedantic, but always worth noting. Phosphorus is a 5A element, so we have 5 valence electrons. So we write phosphorus 1, 2, 3, 4, 5. 5 dots. Does this example make sense to everyone so far? Does this make sense to everyone so far?
Hey, Professor?
Yes.
When you place the dots, is it how many times you go around?
No, it's how many total dots.
Oh, okay.
Yep, so do you notice how for silicon we have 4 valence electrons, so we have 4 total dots? And likewise for phosphorus, we have 5 total dots. Not really. It doesn't matter how you place them as long as the total number of valence electrons that you're noting is correct.
Okay, thank you.
Yep, perfect. Any other questions I can address? If not, let's keep going. So we know elements in the same group have the same number of valence electrons. Let's now look at ionization trends for cations and anions using the octet rule. So we know in the octet rule, atoms gain, lose, or share electrons to reach noble gas configurations, which are 8 valence electrons. This is why 1A or 3A elements form cations with charge equal to their group number. So thinking about this from a Lewis dot perspective, we have sodium with 1 valence electron, in other words, neon 3s1. And when sodium loses its valence electron to form sodium plus, it now has a complete noble gas configuration of neon. So it has a full valence shell. So I'm going to draw the inner shell in a slightly different color, just to show that this neon inner shell is completely full. So we lose electrons to generate noble gas-like configurations, and the number of electrons lost is equal to the charge of our cation. We want to lose 1 electron in sodium because it's a 1A element with 1 valence electron, so we form sodium plus 1. Likewise, group 5A through 7A elements commonly form anions with charge equal to the group number -8. So why the group number -8? So let's look at chlorine. Chlorine is a 7A element, and it has a total of 7 valence electrons. So in order to reach a full valence shell, 8 valence electrons, how many electrons do I need to add? How many electrons do I need to gain? How many electrons do I need to add to chlorine to get a full shell, to get 8 valence electrons? How many electrons do we need to gain?
1.
1, exactly right. So that in turn gives us the following. So we have our full valence shell, and because we gained an electron, we have a noble gas-like configuration, and we have a charge of -1. So chlorine prefers to form chloride. So overwhelmingly, your cation or anion will have a noble gas configuration. Perfect. So we can use the Lewis dot model to help rationalize and explain ionization trends. Wonderful. Now, transition metals typically lose the highest energy s orbital electrons to give cations. So for example, cobalt is going to lose its 4s electrons first. Now, in many cases, you also see the loss of outermost s and d orbital electrons during ionization. So for example, scandium, which we've seen in earlier chapters. So looking at the periodic table, scandium has a configuration of argon 4s2 3d1. If we wanted to lose all of our electrons beyond our noble gas core, we'd need to lose our 3 electrons, and that in turn would give us a noble gas configuration for scandium 3+. So transition metals can sometimes lose not just their s electrons, but also their d electrons to generate an ion with a noble gas configuration. Does that make sense to everyone so far? Is everyone comfortable with this idea so far? So we're just rebuilding and reviewing concepts associated with ionization and bonding from the perspective of Lewis dot structures and electron configurations. If there aren't any questions, let's keep going. So we can start to write ionic bonding and ion electron configurations and view ionic bonding from the perspective of the Lewis dot model. So when writing the Lewis structure and electron configurations of cations, you're going to subtract electrons from the cation equal to the charge. For anions, you're going to add electrons to the anion equal to the charge. So for example, potassium generates potassium plus, so we go from 19 to 18 electrons. Chlorine goes to chloride, so we go from 17 to 18 electrons. Okay, now that we have each of our preferred ions, we know that potassium and chloride can form an ionic compound of the formula KCl. So we have potassium plus and one chloride ion. So this is our representation of potassium chloride using the Lewis dot model. So what I want you to do now is I'd like you to predict the charge and electron configuration of sodium and sulfur after ionization. And I'd like you to draw a Lewis dot structure for each parent atom and ion. And I'd like you to predict the formula of the compound formed when sodium and sulfur react. So we're starting off with sodium and sulfur. I'd like you to draw the Lewis dot structure. And then what we're going to do is we're going to draw the Lewis dot structure of each of our cations and anions, and then we'll write the formula of this compound. So we're going to do this first example together. So sodium, which is a 1A element, has 1 valence electrons. Sulfur is a 6A element, so it has 6 valence electrons. So for sodium, how many electrons do we need to gain or lose? What are we doing with our electrons? Are we gaining or losing? To reach a noble gas configuration, does sodium want to gain or lose electrons? Sodium, which is a metal, and it's a 1A metal. Would it prefer to gain or lose electrons?
Gain.
Oh, I would prefer to lose because it's easier to lose 1 electron rather than gain 7. So metals typically prefer to ionize to form cations. So we're going to lose this 1 valence electron. And in turn, if we lost 1 electron, our charge would be sodium plus. Okay, perfect. So in effect, we've gone from, for sodium, we've gone from neon 3s1 to the configuration of neon. Okay, let's look at sulfur. So for sulfur, to reach a full valence shell, in order to have 8 valence electrons, does sulfur have to gain or lose electrons, and how many? So what does sulfur have to do? It has to gain 2 electrons. So it gains 2. So we're going to gain 2 electrons. Okay. So in turn, that's going to generate, since we gained 2 electrons, we're going to generate sulfide, which is S2 minus. Okay, so in effect, from the perspective of electron configurations, we've gone from argon (3s2, 3p4). Oh, sorry, no, this should be neon 3s2, 3p4 to the configuration of argon. Okay, so now that we have our cation and anion established, we take sodium plus and S2 minus, we cross their charges, and that gives us sodium sulfide. So we have 2 sodiums and then 1 sulfide ion. So this is our representation of sodium sulfide using our Lewis dot model. Does this example make sense to everyone so far? Any questions on this example? So let's now take a look at the following problem. I'd like you to predict the charge and electron configuration of each ion and atom formed when you react cesium and phosphorus. And I'd like you to predict the formula of the compound formed as cesium and phosphorus react. So let's work on this example for about 3 to 4 minutes, and then we'll come together as a group to discuss. Mainly what I'm trying to get everyone to see is that when ions are formed, the ion overwhelmingly has a noble gas configuration, and ionization trends in general follow the octet rule. So let's work on this example for about 3 to 4 minutes, and then we'll discuss. And don't be shy to submit your response in the chat for the preferred charge of each ion and the formula of the ionic compound generated by reacting cesium and phosphorus. And make sure just to double check the group number of phosphorus to predict the ion charge. And the charge for cesium I see in the chat is perfectly correct. Spend another 2 minutes on this example, and let's try to get a few more responses in the chat. And the responses I see in the chat look great so far. We'll discuss in about another minute. Okay, so let's discuss this example. So for cesium, it's a group 1A element. So we're going to go from cesium. Are we going to gain or lose electrons? And if so, how many? For cesium, are we going to gain or lose electrons? And how many are we going to gain or lose?
You lose one electron.
Yep, exactly right. We're going to lose one electron, and that in turn generates cesium plus. So we have, in effect, looking at our periodic table, let's write out the configuration of cesium. So we went from xenon 6s1 to xenon. Perfect. So phosphorus is a 5a element. So we have initially 5 valence electrons. And how many electrons are we going to gain or lose? How many electrons are we going to gain or lose? And don't be shy to type it in the chat or share your responses verbally. How many electrons are we going to gain or lose? For phosphorus, we need to gain 3, exactly right. 1, 2, 3. So we need to gain 3 electrons. And that in turn gives us phosphide, which is phosphorus 3 minus. So now that we have that all set up, let's write out the configuration for phosphide. So for phosphorus, we initially started off as neon 3s2, 3p3, and then we went to a configuration of argon. Okay, now crossing our charges. So crossing our charges for cesium plus and phosphorus 3 minus. We have 3 cesium pluses for every 1 phosphide anion. Perfect. Any questions on this example? Any questions on this example? Okay, so let's talk about a really key point in ionization. So it typically actually costs energy to ionize an atom. And energy is released when atoms gain electrons. Now this process overall is more facile when ionization gives a noble gas configuration. But, and this is really key to this idea of ionization, the major driving force for ionic bond formation is the generation of an ionic bond. So the real sort of energetic payoff is the fact that our cation and anion can engage in a very strong electrostatic interaction. And it's this strong electrostatic interaction, this idea that ionic bonds are very stabilizing. So even if ionization costs us some energy to ionize both our cation and anion, the payoff of forming an ionic bond is so energetically favorable that it drives the process forward. So ionic bond formation really is our driving force. Okay. So let's talk next about ionic compound formation and discuss this idea of lattice energy and the Bohr-Haber cycle. So first and foremost, forming stable ionic compounds from neutral elements is typically exothermic. It releases energy. If you react sodium and chlorine gas, you're going to see a large amount of energy generated. Likewise, ionizing a metal to a cation, removing electrons, is endothermic. It costs energy. Ionizing a metal to form an anion is exothermic. This is known as electron affinity. Now, if we add up our ionization energy and electron affinity, we would predict that forming sodium chloride would be endothermic. However, this ionization is just the first step. It's not the end-all be-all. Because there's another key step that we're missing in this Hess's law calculation, and This key step is known as lattice enthalpy. It's where the ions are combined in the gas phase to yield our solid ionic compound. And this is known as the lattice energy or lattice enthalpy. And this lattice energy or lattice enthalpy is very exothermic. And the combination of your ions to form an ionic compound is highly favorable by enthalpy. Okay, so how do we figure out the lattice enthalpy then? So applying Hess's law, if we add up our lattice energy, our electron affinity, and our ionization energy, we get the enthalpy of reaction. And in turn, if we know our ionization energy, electron affinity, and enthalpy of reaction, we can calculate our lattice energy. Okay, and again, what is the lattice energy or lattice enthalpy? It's the energy released when gaseous ions combine to form an ionic compound. It's very exothermic. Okay, just to be very specific with our definitions before we start to perform calculations, the ionization energy is, again, the energy required to remove an electron from an atom in the gas phase. Now, it may seem like I'm emphasizing this unnecessarily, but remember all the way back in the thermochemistry chapter, enthalpy depends on physical state. So we'll need to keep this gas phase stipulation in mind. As always, ionization energy, the energy required to remove an electron, is endothermic. It costs energy to remove an electron. Electron affinity, as we discussed last chapter, is the energy released or absorbed when an electron is added to an atom, again in the gas phase. Electron affinity values are almost always negative, and electron affinity is almost always an exothermic process. Now, we can combine each of our steps into what is known as the Born-Haber cycle, where we're generating an ionic compound from pure elements. So if we think about the Born-Haber cycle as a series of steps, the first step that we need to take, so let's suppose we want to model the reaction of sodium and chlorine to generate sodium chloride. So the first thing we need to do is we need to convert all of our elements into the gas phase using the tabulated enthalpy of vaporization or sublimation. So as an example, we'd have to take bromine from the liquid to the gas phase, and liquid to gas phase transitions, that's known as the enthalpy of vaporization. To solve the problem at hand, for example, we need to take sodium, solid, and convert it to sodium in the gas phase. Okay, so to go from solid to the gas phase, we'd have to use the enthalpy of sublimation. Chlorine we don't have to worry about because chlorine is already in the gas phase. Okay, next, now that we have gaseous elements, we need to dissociate each of our gaseous elements into gaseous atoms. The reason for that is we want to be able to use our tabulated ionization energies and electron affinities. And again, the whole motivation behind this process is using Hess's law. We're using tabulated enthalpy values that we can look up to calculate the enthalpy for each step in forming our ionic compound. And by calculating the enthalpy for each step, we can in turn solve for and determine our lattice enthalpy. So this is a beautiful application of Hess's law in relation to the other concepts that we've learned so far this semester. Okay, so bond enthalpy, in order to actually go from gaseous elements to gaseous atoms, we need to use our bond enthalpy, which is the energy required to dissociate a bond to give atoms in the gas phase. So we're breaking a bond in the gas phase. And this is important. Before you use the bond enthalpies, you need to have your species in the gas phase. So for example, if we wanted to look at bromine atoms in the gas phase, we'd first have to vaporize our sample, then we'd dissociate our bond. In the case of chlorine, we'd have to, since chlorine's already in the gas phase, we can use our bond enthalpies with no modification. Now, again, why are we generating gaseous atoms? We need gaseous atoms to use our tabulated electron affinity and ionization energy values. So we've taken chlorine and we've put it into the gas phase and we've broken up chlorine into its component atoms. Wonderful. Now, one thing that we do have to keep in mind here is that when we're making sodium chloride, so we're going from sodium solid plus 1/2 chlorine gas leads to sodium chloride solid. How many atoms of chlorine, how many ions of chloride do we actually need? If we're following Hess's law here, and if we're looking at our chemical equation, how many chlorine atoms do we actually need? How many chlorine atoms do we actually need? We only need 1. So we're going to modify our equation in order to produce 1 mole of chlorine gas. And since we're dealing with half the molecules of chlorine, we take our bond enthalpy and we multiply it by 1/2. Perfect. So now at this stage, after using the enthalpy of sublimation for sodium and the bond enthalpy for chlorine, we now have chlorine gas and sodium atoms in the gas phase. So we have both of our atoms in the gas phase. Now what we need to do is we need to ionize each gas. We need to generate the ions that we're going to combine together to make our ionic compound. So we use the electron affinity for anion formation by gaining electrons. And just to make sure that we're clear here, this electron affinity is per atom. And in this case, how many chlorine atoms are we ionizing? How many chlorine atoms are we ionizing? One, exactly right. So it just turns into negative 349 kilojoules. I always want you to do this little check just to make sure, well, how many atoms am I ionizing? How many atoms do I need? This is the nuance that's critical in Hess's law problems. Now, continuing on, we use ionization energy for cation formation as we are losing electrons. So we use our tabulated ionization energy for sodium. Now again, make sure you account for the number of ions in your ionic compound. So we have 1 sodium ion and 1 chloride ion. So then each of our enthalpies are multiplied by 1. So now that we have our ions in the gas phase, we're going to combine the gaseous ions to give a solid ionic compound. And this is our lattice energy or lattice enthalpy. So using Hess's law, if we add up the enthalpy of each step, we can then solve for the lattice enthalpy. And that gives us that our lattice enthalpy, otherwise known as delta H lattice, is equal to the enthalpy of formation minus the enthalpy of ionization minus the bond enthalpy minus the electron affinity minus the enthalpy of sublimation. So we essentially have a way of calculating lattice enthalpy from these tabulated values. Pretty cool, right? Then we can even go farther and compare our lattice enthalpy to the literature lattice enthalpy measured through another method. Okay, so this seems like a lot of steps. Let's show practically how we solve a Hess's law problem and a Bohr-Haber cycle problem. just to help you visualize how each step fits into the Bohr-Haber cycle. So pretend initially we're starting with sodium, solid, and chlorine gas. So first things first, we're going to go from sodium solid to sodium gas. In that case, we use our enthalpy of sublimation for sodium. Next, we break down chlorine gas into its component atoms. So we use 1/2 delta H for our chlorine-chlorine bond. We're using half of our bond enthalpy. Then we ionize our sodium to sodium plus. This is the enthalpy of ionization energy. Then we ionize our chlorine. This is the delta H of electron affinity. And then finally, this super exothermic step is our lattice enthalpy. This is delta H lattice. This is where we're combining our gaseous ions to generate our ionic compound. And in this net process, we've gone from our reactants to our products, and we can relate the total enthalpy of each of these steps to the final minus the initial enthalpy values. And this is known as the enthalpy of formation for sodium chloride. So if we're writing this out mathematically, the enthalpy of formation of sodium chloride is equal to, and now we just add up each of our steps, the enthalpy of sublimation of sodium plus 1/2 the enthalpy of a chlorine-chlorine bond plus the enthalpy of ionization energy for sodium plus the enthalpy of electron affinity for chlorine plus the lattice enthalpy. And now all we have to do is find these tabulated values, punch them into our equation, and we can solve for the lattice enthalpy. So does this make a little bit more sense now that you've seen the Bohr-Haber cycle from the perspective of an energy diagram, just like we did for Hess's law? So this is a nice overview, but let's show how we actually solve problems using the Bohr-Haber cycle and Hess's law. So first and foremost, let's suppose we're asked to calculate the enthalpy of formation of sodium chloride from its elements. So to do that, we are going to first think about what equation that we're aiming for. So we're taking sodium solid plus 1/2 chlorine gas leads to sodium chloride solid. This is the equation for the enthalpy of formation because we're forming sodium chloride from our component elements. In order to generate our enthalpy of formation expression, let's think about each of the steps necessary in the Bohr-Haber cycle. So first, we're going to go from sodium solid to sodium in the gas phase. We're going to use the enthalpy of sublimation, which is 107.3 kilojoules per mole. Next, we're going to take our chlorine gas and dissociate our chlorine-chlorine bond to yield chlorine atoms. This is the bond enthalpy of our chlorine-chlorine bond, which gives us 122 kilojoules per mole. Third, now that we have our gaseous atoms, we're going to ionize sodium to yield sodium plus in the gas phase. This is our delta H of ionization energy, which we're given in this case to be 495.8 kilojoules per mole. For step 4, we're going to take chlorine in the gas phase, and we're going to pick up an electron to generate chloride in the gas phase. This is the enthalpy of electron affinity, which is negative 348.6 kilojoules per mole. Finally, in our last step, we're going to take each of our gaseous ions and combine them together to generate our solid ionic compound. This is the lattice enthalpy, and the lattice enthalpy in this case is negative 787 kilojoules per mole. Okay, so if we add each of our steps together and if we add each of our enthalpies together, we see that sodium in the gas phase cancels. Chlorine in the gas phase cancels, and both of our ions cancel, and we're left with our net equation of sodium solid plus 1/2 chlorine gas leads to sodium chloride solid. And now all we have to do is we have to take each of our enthalpies and add them together, and that gives us an enthalpy of formation of so we have 107.3 plus 122 plus 495.8 minus 348.6 minus 787, and that gives us an enthalpy of formation of negative 410.5 kilojoules per mole. So the Bohr-Haber cycle is a very pure application of Hess's law to solve for an unknown enthalpy. Does this example make sense to everyone now that you've seen the Bohr-Haber cycle in action? Sure. So what we're going to do is we're going to take 107.3 plus 122. You'll be given the chemical equations, yes. Plus 495.8 minus 348.6 minus 787. And that gives us negative 410.5 kilojoules per mole. And just to be 100% specific here, you'll be given the chemical equations and their enthalpies. You will not necessarily be given a guide on how to add these equations together. That's what I'm expecting you to learn in this section and to be able to apply on the exam. Does that make sense? Okay, any questions on this idea? Any questions? Okay, so to test and to help provoke some questions and to make sure everyone's comfortable with this idea. So if you want to see this idea of enthalpy of reaction graphically, here are each of our steps once again. So we have the enthalpy of sublimation. We have the enthalpy for our bond, 1/2, because we're taking half of a chlorine molecule. We have our enthalpy for our ionization energy. We have our enthalpy for our electron affinity. And finally, we have our enthalpy. Whoops, one moment. And finally, we have our lattice enthalpy. Allow me 1 second. There's a small delay with OneNote. So finally, we have our lattice enthalpy. Sorry for that delay. So if we add up each of these individual steps together, that gives us our enthalpy of formation for sodium chloride. Okay, so now that we have an idea of how the Born-Haber cycle works, I would encourage you, if you're stuck on any of these questions, to just start drawing a picture and making sure that everything cancels out and yields your desired equation, just like any Hess's law problem. But in order to provoke some more questions and in order to help everyone have an opportunity to try solving these problems similar to what you'd see on an exam, I'd like you to work through the following example where you're asked to calculate the energy released in kilojoule per mole when sodium iodide is formed, given the enthalpy of vaporization of sodium, the ionization energy of sodium, and in this case, we're given the sum of the enthalpy of dissociation and sublimation of iodine is 214 kilojoules per mole. And then the electron affinity of iodine is negative 295 kilojoules per mole. And the lattice energy of sodium iodide is negative 704 kilojoules per mole. So first things first, I would write my component equations. Then you manipulate your equations and add them together using Hess's law to give you this final desired equation. So let's take about 6 to 7 minutes to work through this example. And in the end, you'll be able to report the enthalpy of formation for sodium iodide from this given set of data. Hess's the Born-Haber cycle is wonderful because it's a great test question for not only testing your understanding of Hess's law, but your understanding of ionization energy, electron affinity, bond enthalpy, and lattice enthalpy. It's a wonderful sort of comprehensive problem, and that's why you should be 100% confident on your final solving at least one of these questions. And if you have any questions or if you have a proposed solution to this problem, don't be shy to message me in the chat. Oh, this should be sublimation. Good catch, good catch. Yeah. So this is for the solid to gas transition for sodium. Okay, so given the following pieces of data, let's try to calculate our enthalpy of formation. And if you have any questions on any of the steps, I'll be happy to answer them. We'll discuss these examples in about 6 minutes. And we'll discuss this example in about another 5 to 6 minutes. And if you have any questions at all, or if you'd like to share your proposed solution verbally or using the annotate features or in the chat. I'd be happy to provide feedback. I find a lot of the questions on these sorts of problems come out when you start thinking and working through a problem on your own. Now, one thing I do want to draw your attention to, and just keep in mind, think about how many iodine atoms are present in our product. You may have to modify some of these enthalpy equations and modify some of these enthalpies for your desired enthalpy of formation expression. And we'll discuss this example in about another 4 minutes. And I'd like to see a few proposed responses in the chat, and then we'll discuss. And if you're stuck at any point, I'd be happy to provide feedback and answer your questions. And remember, writing out your equations and adding them up is the fundamental way to get through Hess's law problems. So the enthalpies I provided to you for iodine have combined the enthalpy of 2 steps together. And your job is to write that equation. And keep in mind that when I'm referring to the enthalpy of dissociation and sublimation of iodine, iodine has the formula I2. And you may want to compare that to the amount of iodine that you actually need in your enthalpy of formation reaction. So let's continue working through this problem. Did I address your question? Was I able to address your question, or is there a part that I can follow up on? Perfect, perfect. So let's spend about another 3 minutes on this example, and then we'll discuss. And let's try to get a few responses in the chat, and then we'll discuss. And if you have any proposed responses, don't be shy to submit them in the chat. Just making sure everyone has enough time to work through the problem, arrive at their conclusion, so that way when we go through the solution, we're able to compare and discuss. Okay, so let's discuss this example. So first and foremost, let's write out my equation. So for sublimation, we're going from sodium solid to sodium gas. This is our enthalpy of sublimation, which is 107 kilojoules per mole. The ionization of energy of sodium, which is going from sodium gas to sodium plus in the gas phase. This is the enthalpy of ionization energy, which is 496 kilojoules per mole. We have the enthalpy of dissociation and sublimation for iodines. We have I2 solid leading to I2 in the gas phase. This is the enthalpy of sublimation. And the enthalpy of dissociation is going from iodine in the gas phase, I2, to 2 iodine atoms in the gas phase. This is the enthalpy of our bond enthalpy, otherwise known as our enthalpy of dissociation. And together this enthalpy is 214 kilojoule per mole. Now, this is our first juncture, and this is the only tricky part of this problem. How many iodines, how many iodine atoms do we need in sodium iodide? Do we need 2 iodine atoms or 1? 2 or 1? 1. So then what do we have to do to this equation? What do we have to multiply our equation by? 1/2, exactly right. And in turn, that means our enthalpy gets multiplied by 1/2. Very good, perfect. So, continuing on, the enthalpy associated with the electron affinity of iodine. So iodine in the gas phase going to I minus is equal to negative 295 kilojoule per mole. And then finally, the lattice enthalpy, which is combining iodide in the gas phase and sodium plus in the gas phase to yield sodium iodide solid. That lattice enthalpy is negative 704 kilojoules per mole. So adding our equations together for each step in the Bohr-Haber cycle, sodium cancels, iodine cancels, iodide cancels, sodium plus cancels, and we're left with sodium solid plus 1/2 iodine solid leads to sodium iodide solid. So adding our enthalpies together, that in turn gives us, so 214 over 2 plus 107 plus 496 minus 295 minus 704. That gives us an enthalpy of formation equal to negative 289 kilojoules per mole, which is still quite exothermic. the majority of the stable isolable ionic compounds that you will encounter will have a negative enthalpy of formation. A positive enthalpy of formation for an ionic compound highly suggests that that ionic compound is unstable. So if we actually look in the literature for sodium iodide, the enthalpy of formation for sodium iodide, we get a literature enthalpy of formation of about 288 kilojoules per mole. So this Born-Haber cycle, or Hess's law method of calculating the enthalpy of formation for sodium iodide, is quite accurate. So any questions on this example? So I wrote out the equations for each step, determined how many atoms of each element I needed in my final ionic compound, modified my equations accordingly, then I added my equations together, added my enthalpies together, and that gave me my final enthalpy of formation. Does this make sense to everyone? Any questions so far?
On the sublimation of iodine,
Yes.
we don't add the 1/2 in the front, as in like before you do the multiplication, because of the 1/2 that's in the equation?
Oh yeah, so this 1/2 would be applied to everything. So it'd be 1/2, 1/2, 1/2, and then just one iodine, because 2 times 1/2 would give us 1. Yep, so the 1/2 would be applied throughout. That's how we end up with this 1/2 iodine in our final equation. Did that answer your question?
Yeah, I got it. Thank you.
Okay, perfect. Sublimation, solid to gas. Ionization, remove an electron. Electron affinity is gain an electron. Bond enthalpy, gaseous molecule to gaseous atoms. And lattice is combining ions to give a solid ionic compound. Did that answer your question in the chat? Did that help clarify some things? Yeah, it's always important to get familiar with what each of the phrases represent in an equation form, but that's okay. It's just because many standard exams, such as the ACS, may give you some of these equations in word form. So we've seen an example, we've worked on an example. Let's apply what we've learned, and let's attempt a capstone example. And I'd ask you to calculate the lattice enthalpy for magnesium chloride using the following information. And the only thing that's new about this problem is that this time we have 2 ionization energies for magnesium. One, and you'll have to figure out and recall our equations for the first and second ionization energy. So write out your equations, set up your enthalpy of formation calculation. You're given the enthalpy of formation, and your goal is, given the enthalpy of formation and all of these other reaction enthalpies, your job is to calculate the lattice enthalpy for magnesium chloride. And we're going to compare the lattice enthalpy of magnesium chloride to sodium chloride or sodium iodide. And we'll see something pretty interesting. So let's get started on this example. We'll spend about 6 to 7 minutes on this example, and then we'll come together as a group to discuss. Yep. Just make sure your physical states are more accurately defined. Remember, enthalpy of formation is combining elements in their standard state to generate a compound. Yep, and the response I see in the chat for the enthalpy of formation expression looks great so far. So let's start writing out our equations, combining our enthalpies, and if we have any questions, I'd be happy to address them. And don't be shy to share your responses in the chat, verbally, or using the annotate feature, whatever you prefer. The bond energy expression, you have it reversed. Bond energy or bond enthalpy is the energy to break a bond in the gas phase. Yep, exactly right. Yep, and the responses I see in the chat look great. If we need 2 chlorines, look and see how many chlorines are produced when you break your chlorine-chlorine bond. In some cases, you may not have to do anything to your equation. Yep, exactly right. But for the bond energy, when you break your chlorine-chlorine bond, you generate 2 chlorine atoms. So as a result, you don't, if you need 2 chlorine atoms, your bond energy already is expressing the enthalpy for a reaction that gives you 2 chlorine atoms. So you can just use the bond energy equation as is, if that makes any sense. And we'll discuss this example in about 4 to 5 minutes. Did I happen to address your question? Yep, that's a correct equation for the second ionization. Okay, we'll discuss in about another 3 minutes. Yep, exactly right. We only needed one sodium in the previous and one chlorine in the previous example. Now we need two. If our equation is already giving us two, we're good to go. Does that make sense? Electron affinity is gaining electrons. So the questions I'm seeing are great. Everyone's on the right track. Let's try to get a few responses in the chat and we'll discuss in about 2 minutes. For electron affinity, we're gaining an electron. So the electron is gained on the left-hand side. Yep, exactly right. And we'll discuss this example in about another minute to minute and a half. Okay, so let's discuss this example. So first, let's look and let's put together each of our component steps. So the enthalpy of sublimation for magnesium, we're going from magnesium solid to magnesium in the gas phase. This enthalpy of sublimation is 147.1 kilojoules. The enthalpy associated with our first ionization energy for magnesium. We're going from magnesium in the gas phase to magnesium plus in the gas phase. This is our first ionization energy, and that's equal to 738 kilojoules per mole. The enthalpy for our second ionization energy, so we're going from magnesium plus to magnesium 2 plus. This gives us an enthalpy of 1,450 kilojoule per mole. Okay, so looking at our bond enthalpy for our chlorine-chlorine bond, we're going from chlorine in the gas phase to 2 chlorine atoms in the gas phase. That gives us an enthalpy of 244 kilojoule per mole. Okay, now let's think a little bit, looking at our enthalpy of formation equation, we're going from magnesium solid plus chlorine in the gas phase to magnesium chloride solid. And we know that our enthalpy of formation is equal to negative 641 kilojoule per mole. And my question to all of you is, how many chlorines do we need? How many chlorines do we need in magnesium chloride? How many chlorines do we need? Two, right? We have 2 chlorines in magnesium chloride. So the 2 chlorines that we produce are perfectly fine. Now let's look at our ionization energy for chlorine. We're taking chlorine in the gas phase, gaining an electron and going to chloride in the gas phase. This has an enthalpy value of negative 349 kilojoule per mole. Now, you may notice I'm getting ready to multiply. Why am I getting ready to multiply this equation? Well, if we have 2 chlorides, if we have 2 chloride ions in magnesium chloride, yeah, this is the electron affinity, yes. So the reason why I'm getting ready to multiply this equation is how many chloride ions do I need to produce? How many chloride ions do I need in magnesium chloride? 1 or 2 or 3 or 4? How many do I need? Looking at magnesium chloride, we have how many chlorides do I need? 2. So what do I need to multiply my electron affinity equation by? What do I need to multiply I see, yeah. What do I need to multiply my electron affinity equation by? 2. Finally, our lattice enthalpy, so delta H for our lattice enthalpy is equal to magnesium 2 plus in the gas phase plus 2 chloride in the gas phase leads to magnesium chloride. This gives us the enthalpy of our lattice enthalpy. So what we're going to do now is we're going to add up all of our enthalpies, and that gives us the following equation. The enthalpy of formation, which is equal to 641 kilojoules per mole, is equal to, and now we're going to add all of our enthalpies together. So let's add that together right now. We have 349 times 2 plus, this is negative 349. Can't forget the sign there. Sometimes OneNote doesn't register that. So we have negative 349 times 2 plus 244. This should also be negative. Plus 1,450 plus 738 plus 147, and that gives us 1,881 kilojoules plus our lattice enthalpy. And now what we can do is that we can solve for our lattice enthalpy by taking our enthalpy of formation minus our other enthalpy values, and that gives us a lattice enthalpy of negative 641 kilojoule per mole minus 1,881 kilojoule per mole, and that gives us a monstrously large lattice enthalpy of negative 2,522 kilojoule per mole. That's an obscene amount of energy generated. Now, this is the lattice enthalpy for magnesium chloride. I'd like you just to compare the lattice enthalpy to something like sodium chloride. In this case, looking at our previous example, where we looked at sodium chloride, our lattice enthalpy for sodium chloride was negative 787 kilojoules per mole. As we can see, depending on the ionic compound, the lattice enthalpy varies. And our goal next is to help explain differences in lattice enthalpy from the perspective of Coulomb's law. So my question to you is, any questions so far? Does this process make sense for calculating the lattice enthalpy? Is everyone comfortable with the Born-Haber cycle? Yes, exactly right. We only had to alter our electron affinity because it was describing the electron affinity for one chlorine atom when we needed two chlorine atoms. Yes, if the others didn't match up, we would alter them as well. Oh, so to show how when you add the equations together, things do cancel. Well, yes, they do cancel. Sure, and that's how you get your final equation for sure. The main point here is just the fact that we can solve for our lattice enthalpy once we've combined our equations together and wrote out a full expression for our enthalpy of formation. Does that make sense? Perfect. So let's now talk about lattice enthalpy and ionic compounds. So let's talk about how does atomic size affect lattice energy. Again, we're going to invoke Coulomb's law, where R can be thought of as the distance between ions. Q1 and Q2 represent the charge of your ions. Now, like charges repel and opposite charges attract. So then, depending on the distance between your ions, depending on your ion size, your lattice enthalpy in general increases as your ionic radius decreases. So if we compare lithium chloride, sodium chloride, potassium chloride, and cesium chloride, lithium plus is the smallest. Because it's such a small ion, the distance between our ions is smaller, and as a result, we have a greater attractive interaction, a stronger ionic bond between lithium and chloride versus, for example, cesium and chloride. So the larger your ions, the weaker your lattice enthalpy. Does that make sense to everyone? Likewise, looking at charge dependence, if we compare, for example, sodium fluoride and calcium oxide, where we have about the same distance, about the same relative ion size. In sodium, we have +1, fluoride is -1. Calcium, we have 2+, oxygen is 2-. Comparing sodium fluoride to comparing sodium fluoride to calcium oxide, which species has the larger lattice enthalpy? Which ionic compound has the larger lattice enthalpy? The ionic compound with the smaller charges or the larger charges? Which ionic compound has the larger lattice enthalpy? The one with the smaller charges or the larger charges? Looking at the data that we have. The larger the charge, exactly right, the larger your lattice enthalpy. So lattice energy increases as the charge of each ion increases. An ion charge has a much larger effect on lattice energy. Perfect, perfect. Now, why does this matter? Why do we care? Well, if we look at different ionic compounds, just in summary, as the ion size increases, lattice energy drops. As the ion charge increases, lattice energy increases. And the kicker for this is that substances with large lattice energies have large melting points. So it's very different. So sometimes for very high temperature reactions, you make like a potassium chloride bath of ionic salts. You're not going to try that with something like calcium oxide. That's to go to an extremely high temperature. So the lattice energy is directly related to the melting point. The larger the lattice energy, the larger the melting point. And in melting, we're essentially separating the ions slightly from their closely packed lattice. Okay, so here's a table of different cation-anion pairs and their lattice enthalpy. As we can see, if we go from ions with a -1 charge to ions with a -2 charge, our lattice enthalpy increases substantially. Okay, so let's apply what we've learned now. And let's try to rank the following in order of increasing melting point. So I'll do this first example. So calcium oxide, we have calcium +2, oxygen -2. Potassium bromide, we have potassium plus, bromine -1. Potassium chloride, we have potassium plus, chlorine -1. Strontium oxide, we have strontium +2, oxygen -2. So step one, I'm going to sort by charge. Charge wins over ion size. So we have the +2 -2 pairing and the +1 -1 pairing. So we have calcium oxide and strontium oxide and potassium bromide and potassium chloride. Next, what we're going to do is we're going to sort by size. So if we compare bromide, which is n equals 4, to chloride, which is n is equal to 3, okay, which species is larger, bromide or chloride? Which ion is larger and as a result will have a lower lattice enthalpy? Which ion is larger, bromide or chloride?
Bromide?
Yep, bromide's larger, ergo potassium bromide would have the smaller lattice enthalpy. Comparing, we have calcium, which when calcium ionizes, it becomes an n is equal to 3, and strontium, when it ionizes, becomes an n equals 4, because this is calcium 2 plus, strontium 2 plus. So which ion is smaller and as a result has the larger lattice enthalpy? Which ion is smaller, calcium or strontium? And as a result, which ion would have the larger lattice enthalpy?
Calcium is smaller.
Yep, calcium's smaller. So as a result, calcium oxide has the largest lattice enthalpy, and strontium oxide has the next largest. Perfect. So now we have our ranking. Any questions on this example? Any questions on this example? So comparing strontium and calcium, ion size impacts. It's not because they're positively charged. They have a +2 charge. So they have a greater charge than, for example, potassium bromide or potassium chloride. So the attractive interaction is going to be stronger. Comparing calcium and strontium, when they lose electrons, their end value, their outermost orbital, is that of the preceding noble gas shell. So then comparing calcium and strontium, calcium is N equals 3. Strontium is N equals 4. Calcium smaller, smaller ion, stronger, closer proximity attractive interactions, larger lattice enthalpy, and in turn, a larger melting point. Does that make sense? Perfect. So let's now work independently or in small groups on the following example, and let's rank the following species in order of increasing melting point. Remember, charge is the first category for assessing lattice enthalpy. Then you look at radius, only after that. And don't be shy to submit your proposed responses in the chat. Consider that you need to look, your line of reasoning is correct, but consider that it's not just the charge of an individual ion in the ionic compound, but the total charge of each ion involved. So there may be some difference between boron nitride and aluminum oxide. You can even invoke size arguments if you prefer as well. And we'll discuss this example in about another 2 minutes. Let's try to get a few responses in the chat and hopefully we can get some revisions. The discussions we've been having in the chat have been working out quite productively. So let's try to put these ideas together. Yes, aluminum would have an N value of 2 since it has a noble gas configuration matching that of neon. Yep. Both of the N values matter. We have to consider both of the ion charges and both of the ion sizes in our consideration. The larger your ions are, the lower the melting point. Smaller ions lead to larger lattice enthalpies and larger melting point. Did that clarify and address your question? So let's discuss this example. So first things first, let's look at each of our ion pairs. So we have beryllium oxide, which has +2 and -2. Boron oxide, which has +3 and -2. Aluminum oxide, which has +3 and -2. And boron nitride, which has +3 and -3. So which of these ionic compounds has the largest charge? So sorting by charge, which of these ionic compounds has the largest cation and anion charge? Which of these species has the largest cation and anion charge? Boron nitride. So boron nitride would have the highest melting point. Okay, now we have a tie in ion charge between boron oxide and aluminum oxide. And my question to all of you, which set of ions is smaller? The ions in boron oxide, which is boron 3+, or aluminum 3+? Which set of ions is smaller? Which set of ions is smaller? Boron oxide, exactly right. And as a result, smaller ions, stronger attractive interaction, larger lattice enthalpy, larger melting point. Okay, finally, beryllium oxide has the lowest ion charges, so it has the lowest melting point. Does this make sense to everyone so far? Any questions on this example? Okay, so we've been firmly in the ionic bonding camp. Let's now move and discuss covalent bonding. So covalent bonding involves the sharing of electrons between atoms. Atoms in general will share electrons to form an octet, 8 valence electrons. Bonding electrons are shared in pairs between atoms participating in a covalent bond and are counted as belonging to both atoms in the bond. So for example, if two hydrogen atoms are forming a bond, it can be written as a set of dots or a line. This set of paired electrons, this pair of shared electrons is known as a covalent bond. And as a result, if we're counting the electrons belonging to each hydrogen atom would be considered as owning 2 electrons to its name. Does that make sense to everyone? So bonds can be written as a pair of shared electrons or a line. Electrons are always shared in pairs. Lone pair electrons or non-bonding electrons are electrons that are not shared between atoms. Lone pair electrons are counted as belonging only to the atoms containing that lone pair. So if we look at hydrochloric acid, for example, we have a bond, we have some shared electrons, and we have some lone pair electrons. Let me give them a different color just to make it easier to see. So these electrons in purple are our lone pair electrons. Now, if we look and we count the electrons belonging to each atom, hydrogen has 2 electrons to its name, 2 shared electrons, while chlorine has 2 electrons shared. And how many lone pair electrons does chlorine have? How many electrons are belonging only to chlorine? How many dots do we see around chlorine that are only belonging to chlorine?
6.
6, exactly, plus 6 electrons as lone pairs. And that in turn gives us 8 electrons, satisfying our octet rule. One thing that I want you to note is that hydrogen follows what's known as the Duet Rule, in that a 1s2 configuration, or 2 electrons, is a stable noble gas-like configuration for hydrogen. And that's because the closest noble gas to hydrogen is helium, which only has 2 electrons. So hydrogen is an exception to the octet rule. Does this make sense to everyone so far? So let's look at water. Let's look at water, H2O. I'll draw out the structure for water. So we have some bonding electrons. We have some lone pair electrons. Now let's count and let's make sure we've thoroughly accounted for the electrons belonging to each atom in this molecule. So hydrogen has how many electrons to its name? How many electrons does hydrogen own? How many electrons are belonging to hydrogen? If it has 1 bond with oxygen.
2.
2, yep. So hydrogen has 2 electrons to its name. What about oxygen? How many total electrons does oxygen have to its name if it has 2 bonds and it has 2 lone pairs? How many electrons are belonging to oxygen? 8. And the hydrogen on the right also has 2 electrons. Wonderful. So we're getting quite good at counting electrons. You're going to need to use this skill a lot. Now, bonding electrons are shared in pairs between atoms, and they're counted as belonging to both atoms. Lone pair electrons are counted as belonging only to the atom containing that lone pair. And as we saw for water, each atom has a complete octet or a noble gas-like configuration. So for example, for water, drawn in the line notation, water would look something like this. I'll draw both portrayals of water just so that way we have a reference point to touch back on later. So as we see, oxygen has 8 electrons total, hydrogen has 2 electrons total. Both of our atoms have a noble gas-like configuration, and our octet rule is fulfilled. Okay, so that's really going to serve as our cornerstone to start to represent the structures of molecules and portray how electrons are shared in terms of bonding electrons and how electrons are localized on atoms as lone pairs. So we're slowly developing the skills that we need to start to draw Lewis structures, to begin to represent the structure of molecules. So it's quite exciting. So let's keep going now, and let's talk a little bit about how bonds can be represented and the different types of covalent bonds. So bonds are commonly written as lines between each atoms. Each line represents one bond, which is 2 shared electrons. If we have one pair of bonding electrons, that's known as a single bond. So for example, a fluorine-fluorine bond is known as a single bond because we are sharing 2 electrons. This can be written as a single line between our fluorine atoms. So just to make sure we're on the same page, if we look at the amount of electrons that are belonging to each fluorine atom, how many electrons belong to each fluorine atom? So if we look at this fluorine atom on the right, how many electrons belong to that fluorine atom? 8. Yep, we have 6 plus 2, which gives us 8 electrons. So we're still fulfilling the octet rule. Now what's really cool is that atoms can share more than one pair of electrons and form multiple bonds between atoms to complete their octet. So for example, 2 pairs of bonding electrons would be a double bond. So oxygen, O2, we'll touch on this in a more nuanced example later on, but oxygen can be drawn as containing a double bond. This can be written as a pair of lines or as a total of 4 electrons shared between atoms. So if we count the amount of electrons belonging to each oxygen atom, how many electrons are considered belonging to this oxygen atom on the right? How many electrons are owned by the oxygen atom on the right? 8, exactly right. We have 4 bonding electrons plus 4 lone pair electrons. That gives us 8 electrons total. Does this make sense to everyone so far? Okay, so let's look at the third type of bonding pattern where we have 3 pairs of bonding electrons. This is known as a triple bond. Nitrogen, in its diatomic form, likes to form a triple bond. In a triple bond, we have 6 electrons shared between our atoms. So if we think about the electrons belonging to this nitrogen on the right, we have 6 bonding electrons plus 2 lone pair electrons, and that in turn gives us 8 electrons total. Okay, there's one exception to the octet rule. Again, hydrogen prefers to form what's known as a duet, where it contains 2 electrons, because hydrogen's adopting the pseudo-noble gas configuration of helium. Okay, So now what we're going to do is we're going to put together all of our ideas associated with covalent bonding, and we're going to talk a little bit about how to draw Lewis structures. So Lewis structures allow us to draw plausible stable structures for a given chemical formula. So most stable structures fulfill the octet rule for each atom. Okay, so for drawing Lewis structures, step 1, you count the total number of valence electrons for all atoms, remembering that the valence electrons are equal to the group number for most main group atoms. If your molecule is a cation, you subtract electrons. If your molecule is an anion, you add electrons equal to the charge. Next, you're going to determine the central atom. Hydrogen is never the central atom, and the central atom is always the least electronegative atom. Then you're going to arrange your atoms as symmetrically as possible around the central atom, keeping in mind that if you're in the first or second row, you can only have a maximum of 4 atoms around each central atom. So no expanded octets for n equals 1 and n equals 2 elements. There can be multiple central atoms, so that you have a little bit of flexibility. Now, first and foremost, you're going to form a single bond, 2 electrons, 1 line, between the central atom and each surrounding atom. Since we formed a bond each, we're going to subtract 2 electrons for each bond formed. Then you're going to place electron pairs around the outer atoms until the octet of all atoms is satisfied or you run out of electrons. Okay? Now, this is where students often get a little bit ahead of themselves. If an octet is not fulfilled and you're out of electrons, then and only then do you convert your lone pair electrons into a double or triple bond. Only use a double or triple bond if it is needed. Sometimes for Lewis structures, I see a ton of double and triple bonds and they're not needed. You only need to use a double or triple bond when you run out of electrons and you need to fulfill the octet of multiple atoms. Once you're done drawing your full Lewis structure, make sure you check that all atoms have a complete octet. Now, this is a nice set of rules. Let's show how these rules are put into practice. So for CF4, first things first, I'm going to do a count. So carbon, which is a 4A element, has how many electrons? How many valence electrons? 4. Okay. Fluorine, which is a 7A element, has how many valence electrons? Sorry. How many valence electrons does fluorine have? 7, okay. And we know that we have 1 carbon atom. And how many fluorine atoms do we have? How many fluorine atoms do we have? 4. So that gives us a total of 32 electrons. Next, we designate our central atom. What's our least electronegative atom? What's our least electronegative atom? Carbon, okay. Then we're going to surround it with our 4 fluorines. Remember, group 1 and 2 elements can have a maximum of 4 surrounding atoms. Then what we're going to do is we're going to form 1 bond each, and we're going to subtract 2 electrons times the number of bonds, which is 4. We have 24 electrons remaining. Now what we're going to do is we're going to add lone pairs to each of our atoms. So looking at fluorine, how many lone pairs do I need to add to get 8 surrounding electrons? How many lone pair electrons do I need to add? How many total lone pair electrons do I need to add? I need 3 lone pairs or a total of 6 electrons. So I'm going to add 6 lone pair electrons to each fluorine atom. So now each fluorine has a complete octet. 6 times 4 gives us 24. We have 0 electrons remaining. Just as a check, each fluorine has 2 plus 6 or 8 electrons to its name. Carbon has 2 times 4 or 8 electrons to its name. The octet rule is satisfied, and we have our final structure for carbon tetrafluoride. Does this make sense to everyone? Does this step-by-step process make sense? Any questions? Okay, let's look at another example, formaldehyde. So carbon is a 4A element, so we have 4 electrons. Oxygen is a 6A element, so we have 6 electrons. Hydrogen is a 1A element, so we have 1 electron. We have 2 hydrogens, so that in turn gives us a total of 12 electrons. What is our central atom in formaldehyde? What is our central atom in formaldehyde? Carbon, yep, exactly right. So carbon is the central atom. We're going to surround it with our remaining atoms. Then what we're going to do, following our procedure, we're going to form 1 bond each. We formed 3 bonds, so we used up 6 electrons. We have 6 electrons remaining. So what atom has an incomplete octet that is an outer atom? You're going to place your lone pairs on your outer atoms first. So what atoms are your outer atoms that we need to fulfill the octet rule for? Oxygen, right? So how many electrons, how many lone pair electrons does oxygen need? 6. So we're going to add 6 lone pair electrons. We have 0 electrons remaining, so we don't have any electrons to put a lone pair on carbon. So then, and only then, we break out our second tool. Step 4, we can convert lone pairs to double or triple bonds. Okay, so then, how many electrons does carbon need? How many additional electrons does carbon need for a complete octet? How many additional electrons does carbon need? 2. So we're going to take one of our lone pairs and we're going to form a double bond. Now let's check our work. So for carbon, we have 2 times 4 or 8 electrons. For oxygen, we have 2 times 2 plus 2 times 2, which gives us 8 electrons. For hydrogen, we have 2 electrons. So the octet rule is fulfilled for all of our atoms. And here we have our final structure. Does this process of drawing Lewis structures make sense to everyone? Any questions on this example? Okay, so let's take a moment and let's try to write out the Lewis structures for the following 2 compounds. And you're welcome to use the annotate tool, or I'd like you to message me in the chat the number of lone pairs that you've drawn in each of your structures. And for the second structure, I'd like you to tell me the number of double bonds in your structure. Just so that way I have a way that you can provide a response in the chat and I can give you feedback. Or if you want, there's this little pen button on Canvas called the Annotate tool, and you're more than welcome to try drawing your Lewis structure. So we'll spend about 4 to 5 minutes on this example, and then we'll discuss. And I really encourage you to use the Annotate tool. If you plan on taking any organic class while we're still online, it would be good to be familiar with how to use the Annotate tool on Zoom, as it's super helpful for talking about structure. It doesn't matter what side you put the lone pair on nitrogen, that's correct. As long as you clearly have the 2 electrons paired together on nitrogen, that's fine. And don't be shy to message me in the chat with or draw your structure using Annotate tool, or message me responses to each of these 2 queries that will help me provide feedback on your structure. And the responses I see in the chat look great so far. And we'll discuss in about another 2 to 3 minutes. Okay, so let's discuss this example. So for ammonia, so nitrogen has 5 electrons to its name. Hydrogen has 1 electron to its name. We have 3 hydrogens. That gives us 3 electrons. So in total, we have 8 electrons to work with. Nitrogen is our central atom. We surround it with 3 hydrogens, and then we form 1 bond each. That uses up 6 electrons. We have 2 electrons remaining, and we place our remaining 2 electrons on nitrogen to fulfill its octet. As we see, nitrogen has 2 plus 6 or 8 electrons, so it has a complete octet. Hydrogen has 2 electrons, another complete octet. Does this example make sense to everyone? Any questions on this first example? Let's look at another example. In this case, sulfur dioxide. So sulfur has 6 electrons, oxygen has 6 electrons, and we have 2 oxygens. That gives us 12 electrons. So in total, we have 18 electrons to work with. So what is our central atom going to be? What is our least electronegative atom? Sulfur. Yep, so we place sulfur in the center. We surround it with our 2 oxygen atoms. Then what we, oh, sorry about that. Then what we're going to do is we're going to form 1 bond each. Okay, so we've used up 4 electrons, so we have 14 electrons remaining. Now what we're going to do is we're going to place our lone pairs on our outer atoms. So each oxygen needs 6 electrons. So we've used up 12 electrons. We now have 2 electrons remaining. Where do our last 2 electrons go? What atom has an incomplete octet? Sulfur. So we place our 2 electrons on sulfur. Now, are there any atoms with an incomplete octet? Have we fulfilled the octet rule for all of our atoms? Sulfur still needs a complete octet, so what we're going to do is we're going to take one of our lone pairs on oxygen and we're going to convert it to a double bond. Now to check our work, oxygen has 6 plus 2, 8 electrons. Sulfur has 2 times 3 plus 2 or 8 electrons. And oxygen has 2 times 2 plus 2 times 2, which gives us 8 electrons. So we've fulfilled the octet rule and we're all good to go. So this is our complete structure, just obeying the octet rule for sulfur dioxide. Now, for those of you who may have read ahead or may have received a more comprehensive coverage of Lewis structures in your preparatory class, you may be feeling a bit odd staring at this structure, wondering something doesn't look right. We'll talk about that actually in a moment. So if you're feeling a little bit uneasy about the way this structure looks, there's a reason for that. Any questions before we move on? Any questions before we move on? So when you have a cationic species, you subtract electrons equal to the charge. Okay, so what does that mean practically? So for H3O+, so H3O+, we have hydrogen, which has 1 electron, and we have 3 hydrogens. So we have 3 electrons from hydrogen. Oxygen, we have 6 electrons. We have 9 electrons, but since we have a +1 charge, we subtract our +1 charge, and that gives us 8 electrons total. So then, with that manifold established, we put oxygen in our center. We surround it with our 3 hydrogen atoms. Then we form 1 bond each. That gives us 6 electrons used. We have 2 electrons remaining. And where does our last lone pair go? Where does our last lone pair go? What atom doesn't have a complete octet? Oxygen, okay. Perfect. So this is a complete structure for H3O plus, but if you have a charged species, you put the entire structure in brackets and you specify the charge, in this case +1. Now let's look at anionic species. When you have an anionic species, you add electrons equal to the charge. So for cyanide, which is Cn minus, carbon we have 4 electrons, nitrogen we have 5 electrons, that gives us 9 electrons plus 1, which gives us 10 electrons. So then, well, there's no central atom in this case, so we have carbon and nitrogen. We form 1 bond each. So we have 8 electrons remaining. We place lone pairs on nitrogen. That's used up 6 electrons. We have 2 electrons remaining. Where do we place our remaining electrons? Where do we place our remaining electrons? Just to make sure everyone's following along with me. Carbon, yep. Okay, now what we're going to do, does carbon have a complete octet? Does carbon have a complete octet? No. So how many more bonds, how many additional bonds does carbon need? How many additional bonds does carbon need? 2. So we're going to take 2 of our lone pairs and convert them into 2 additional bonds. Checking that we've done everything correctly, carbon has 2 plus 6 or 8 electrons, and nitrogen has 2 plus 6 or 8 electrons. The overall charge of this ion is -1, so we put our structure in brackets and we indicate the charge. Do these examples make sense to everyone so far? Do these examples make sense? Okay. So let's talk next about formal charges, which serve as an additional rule in order to draw logical and well-reasoned Lewis structures. So in general, favorable Lewis structures have atoms with small formal charge values, have few atoms with a non-zero formal charge. They place negative formal charges on more electronegative atoms and positive formal charges on less electronegative atoms. And in general, favorable Lewis structures try to avoid placing adjacent negative and positive formal charges. Now, what is formal charge? So formal charge is a description, an approximation for the relative amount of charge on a given atom in a Lewis structure as drawn. It's best defined as the group number of your atom minus the number of bonds plus the lone pair electrons. Okay? So let's take a look at an example. And one thing to note, the total charge of the molecule is equal to the total formal charge of all atoms in that molecule. So for example, if we look at ammonium, which is NH4 plus, looks something like this. So nitrogen, 5 electrons, hydrogen, 1 electron times 4. We have 9 electrons minus 1 because we have a +1 charge. We had 8 electrons to work with. We formed 4 bonds. We had 0 electrons remaining. Let's look at a formal charge calculation. Let's calculate the formal charge of nitrogen. So what is the group number of nitrogen? What is the group number of nitrogen? Five, yep. Okay, and how many bonds is nitrogen forming? 4, yep. And how many lone pair electrons do we have? How many lone pair electrons do we have? 0. Okay, so that gives us a formal charge of nitrogen of +1. So we put a plus next to nitrogen. The formal charge of hydrogen, we have a group number of 1, we have 1 bond, that gives us a formal charge of 0. So as we can see, the formal charge of nitrogen plus the formal charge of all of our hydrogens gives us the total charge of +1. Does that make sense to everyone? Okay, let's look at another example. Ozone, which doesn't look like it has a charge, but that doesn't mean the atoms aren't charged. The molecule can be neutral, but a neutral molecule can have atoms with formal charges. So for ozone, we have 6 electrons times 3 oxygen atoms. That gives us 18 electrons. So what would we like to have as our central atom? What's our central atom going to be? We have plenty of choices for this problem. Oxygen, yep. Okay, now what we're going to do is we're going to form 1 bond each. So we've gone down to 14 electrons. Now we're going to place our lone pair on the outer atoms first. So how many lone pair electrons does this how many lone pairs does this rightmost oxygen need? How many lone pair electrons does the rightmost oxygen need? 6 lone pair electrons. 2, 4, 6. The leftmost oxygen also needs 6, 8, 10, 12. We used up 12 electrons. We have 2 electrons remaining. Where do our last 2 electrons go? The central oxygen, okay. We have 0 electrons remaining. Does this central oxygen have a complete octet? No. So we're going to take one of our lone pairs, and how many additional bonds does this central oxygen need? Oh, it needs 2 additional electrons or 1 additional bond. Yep, perfect. So now checking our work, we see that the octet rule for all of our oxygens has been fulfilled. Let's calculate now the formal charge of each oxygen. So the formal charge of this oxygen on the left, what is the group number of oxygen? What is the group number? 6, okay. How many bonds are we forming for oxygen? No, just for this oxygen on the left, how many bonds is this oxygen on the left forming? Just 1. Yep, that's okay. How many lone pair electrons, not lone pairs, but lone pair electrons are found on the leftmost oxygen? Six. Yep, exactly right. That gives us a formal charge of -1. That already begins to set off some alarm bells. Wait, what's going on here? This molecule's neutral. Well, let's look at the formal charge of this middle oxygen. So again, our group number is 6. And how many bonds is this middle oxygen forming? How many bonds is this middle oxygen forming? 3, yep. And how many lone pairs? How many lone pairs are on this middle oxygen? How many lone pair electrons are on this middle oxygen? 2, yep. That gives us a formal charge of +1. Okay, so we put a +1 charge on the central oxygen. Finally, for the rightmost oxygen, our formal charge is equal to 6. And now how many bonds are we forming? 2, okay. And how many lone pair electrons do we have? 4, yep. So that gives us a formal charge of 0. And you don't have to put the formal charge of 0. You only have to specify the non-zero formal charges. Okay, so now just to add up each of our formal charges, our total charge is equal to the total formal charge of each atom, which is -1 plus 1 plus 0. That gives us a total charge of 0. As we can see, if we add up all of our formal charges, it matches the total charge for our molecule, which is 0. Does this make sense to everyone so far? Does this make sense to everyone? Perfect. So let's now look at an example. I'd like you to draw the Lewis structure for each molecule and assign formal charges to each atom. Note, we haven't yet covered expanded octets. So if you are drawing an expanded octet structure, please note that in the chat so I can provide feedback that's more appropriate to your response. Okay, so I'd like you to draw the structures and then tell me in the chat what is the formal charge of each of the atoms involved in that structure. And we'll discuss this example in about 6 minutes. And we'll discuss this example in another 4 minutes. So let's try to get a few responses in the chat. And if you'd like, you can click that little pen button called the annotate tool in your Zoom view, and you'd actually even be able to draw your proposed structure out on the whiteboard. And if you need any help with working through any of these Lewis structures, I'd be more than willing to have an office hour session where we go through with the annotate tool and we work through problems as well. Let's try to get some responses in the chat for the formal charges of each atom, specifically our central atoms. And that'll give me a sense of whether you're on the right track drawing your Lewis structures. If not, we'll discuss in about 3 minutes. Yep, and the responses I'm seeing in the chat look great so far. And the responses I see in the chat for the formal charge assignments look great. We'll discuss in about 1 minute. For which atom? For nitrogen, I would double check your group number and formal charge calculation. Yep, exactly right. That formal charge assignment that you recalculated is perfect. Yep, that calculation, the 1/2 doesn't apply to the bonding electrons and the lone pair electrons. It only applies to the bonding electrons if you're using that form of the equation. So let's discuss this example. So for nitrate, NO3-, nitrogen contributes 5 electrons, oxygen contributes 6 electrons times 3, which gives us 18 electrons. So we have 23 electrons plus 1 because we have a -1 charge. That gives us 24 electrons. Now, would the class like to help me out here? What is the central atom in this structure? What is the central atom in this structure? Nitrogen, yep. We surround it with our 3 oxygen atoms, and then we form 1 bond each. That gives us 18 electrons remaining. How many electrons do our outermost oxygen atoms need for a complete octet? 6, 2, 4, 6, 8, 10, 12, 14, 16, 18. We burn through all of our electrons. Okay, now this looks great, except you look at nitrogen, and is nitrogen very happy with this so far? Does nitrogen have a complete octet? No. So we're going to take one of our lone pairs. It really doesn't matter which one. It does not matter at all. And we're going to convert it to a double bond. Now, does nitrogen have a complete octet? Does nitrogen have a complete octet? Yes. Okay, let's now do some formal charge calculations. So for the topmost oxygen, our formal charge for our topmost oxygen, which I'll call oxygen top, is equal to the group number 6 minus the number of bonds, which is 2, plus the number of lone pair electrons, which is 4. And that in turn gives us a formal charge of 0. The formal charge of the oxygen on the left, it's going to be the same as the oxygen on the right, is equal to 6 minus our bonds, which is 1, plus our lone pair electrons, which is 6. And that in turn gives us a formal charge of -1. Well, we have some negative formal charges, so there must be a positive formal charge. So in turn, let's figure out the formal charge of nitrogen. So nitrogen's group number is 5. How many bonds is nitrogen forming in nitrate? How many bonds is nitrogen forming? 4, yep. And we have 0 lone pair electrons. That gives us a formal charge of +1. Okay, now looking at all of our formal charges, if we look at our total, we have -1, -1, +1. That gives us a total charge of -1, which matches the observed total charge of nitrate. Does this example make sense? Any questions on this example? Okay. Looking at Thianil Chloride, a very smelly reagent, but useful. Let's count our electrons. Sulfur has 6 electrons, oxygen has 6 electrons, chlorine has 7 electrons, and we have 2 chlorine atoms. That gives us 26 electrons to work with. What is our central atom going to be? What is our central atom going to be? What's the least electronegative non-hydrogen atom? Sulfur, yep. So sulfur is going to be our central atom. We surround it with our remaining atoms, and then we form 1 bond each. 1, 2, 3. That gives us 20 electrons. Now, how many electrons do our outermost chlorine and oxygen atoms need for a complete octet? How many electrons do I need to add? Yep. So we need a total of 6 additional electrons for each of our atoms to have a complete octet. Right? Because each of our atoms have 2, we need 6 additional to make a total of 8. Does that make sense? Did that address that question? Okay, so now this all looks great. We've used up 18 electrons. We have 2 electrons remaining. Where do we place our last 2 electrons? Where do we place our last 2 electrons? Sulfur. So 1, 2, we've used up all of our electrons. We've fulfilled the octet rule, but, and now this is a bit of an odd stipulation, let's look at our formal charges. So the formal charge of chlorine, we have our group number of 7 minus our 1 bond plus our 7 valent, 1 bond plus our 6 lone pair electrons gives us a formal charge of 0. For the formal charge of sulfur, our group number is 6. And how many bonds is sulfur forming? How many bonds is sulfur forming? 3. And how many lone pair electrons does sulfur have? 2. That gives us a formal charge of sulfur of +1. Let's look at the formal charge of oxygen. Oxygen has a group number of 6. We form 1 bond. We have 6 lone pair electrons. That gives us a formal charge of -1. So this is a fine structure, but it's not the best structure. So if we wanted to minimize formal charges, what would be the best way to minimize formal charges? So we have an excess of electrons on oxygen. Sulfur needs additional electrons, and sulfur is one of the rare elements. Since it's n equals 3 and above, it can actually form more than just 4 bonds. So as we'll talk about, and this is a prelude for our tomorrow's lecture, the true structure of thionyl chloride actually invokes an expanded octet. And the reason why this expanded octet structure is so preferred is that this structure minimizes formal charges. So that's a little teaser of what we're going to be covering next class session. So that's the end of the planned lecture for today. So I'm just going to pause the recording.